Hello friends, how are you? One of the objectives of a good code design is to have a fast and efficient encoding and decoding methodologies. So far, we have dealt with the efficient generation of the linear block codes using a generator matrix. My question is that, is it possible to detect a valid code word using a similar concept? The answer is yes. And such a matrix is called as a parity check matrix, and it is represented by H. In this video lecture, we are going to see the methodology how we can calculate the parity check matrix, and also we will see the error detecting and the error correcting capabilities for the linear block codes. This is the question I have taken. This is the generator matrix, and this generator matrix is represented by I and coefficient matrix P. Okay, and from here we can say that there are 6 columns and 3 rows. Therefore, we can say that this n equals to 6 and k equals to 3. Okay, question here is from the given generator matrix. We have to calculate or generate all the possible code words. We will also see, which is our main primary objective of this video, is to find the parity check matrix H, and also find the error detecting and correcting capabilities. Okay, before going to the finding the parity check matrix, we will see the error detecting and correcting capability of the given problem for the linear block codes. My request is to see one video previously I have given, where I have calculated all the possible code word from this generator matrix, and from there video you can see this table that from the 3 bits k equals to 3 bits, I have generated these 8 possible combinations of the code word. Now, first we will calculate what is the error detecting capability and error correcting capability. Then we will go to the calculation of the parity check matrix. Okay, from this table, for this table, if you want to see how the complete code word had been generated, I have given a description of that video in my description box. You can check it from there. This is the table of the complete code vectors of all the possible 8 combination of the code word. This red box, this column of the red box, you can see here shows the Hamming weight. Hamming weight is nothing but the number of the non-zero vector in the code word, present code word. Okay, we will calculate the Hamming this Hamming weight, and from this Hamming weight of all the possible code vector, we will calculate the d minimum here. D minimum, what is the d minimum? D minimum is the minimum Hamming distance, is the minimum Hamming weight of all the possible code word except 0. From this column we can see that the 0 is the least, but we will not take the 0. 3 is the minimum Hamming weight of all the possible code word. Therefore, from the column we can see that d minimum is equal to 3. Okay, let us now go and see the error detecting and error correcting capabilities of the linear block code. This is the formula for calculating the error detecting capability for the linear block code. D minimum is given as greater than or equals to s plus 1. And what is this s? This s is shows the number of error that that can be detected. Okay, from the previous slide we have seen that dmin is equals to 3. If you substitute dmin here, our objective is to calculate s. Okay, so dmin, after substituting the value of dmin equals to 3 here, and let us calculate the s here, s plus 1, and 3 minus 1 greater than s 2 greater than S, or S is less than or equals to 2. What this S less than equals to 2 shows that it can detect up to maximum 2 errors per word. Okay, this is we have calculated from the dmin. Okay, let us now move forward and let us see the error correcting capability of the linear block code. Error correcting capability of the linear block code is given by d minimum greater than or equals to 2t plus 1. This error correcting capability shows how we can correct up to 3 errors per word. T is the T errors we can correct. Okay, from the previous calculation we have seen that this d min equals to 3. Substituting 3 here, 3 greater than 2t plus 1, 3 minus 1 greater than 2t, and 2 greater than 2t. Okay, therefore we can see that 2 cancel, or we can say 2 by 2 greater than t, or t less than equals to 1. Therefore, what this t less than equals to 1 shows that we can correct up to maximum 1 error equals to, or maximum 1 error per word. Okay, in the previous slide and this slide we have seen the how to predict the error detecting and the error correcting capability of the linear block code for the given generator matrix. Okay, let us now move our objective of calculating the parity check matrix. And as we have seen, this parity check matrix, H is an important parameter. With this help of this parity check matrix H, we can easily detect a valid code word. Okay, we will see that in syndrome decoding. Okay, let us see how to calculate parity check matrix from the generator matrix. The generator matrix we have taken in the question itself. Let us see that thing. H tends to this H we have to calculate from the generator matrix. Okay, the generator matrix from the previous question is 1 1 0 0 0 1 1 0 1 0 0 0 1 1 0 1 1 1 0. From here, earlier we have seen that G matrix is represented by I matrix and the coefficient matrix P. Okay, this I identity matrix is given by what? I matrix is given by 1 0 0, and this 0 1 0 and 0 0 1. This is the I matrix. Leaving the I identity matrix, we are having the coefficient matrix P. Okay, P is what? 0 1 1 1 0 1 1 1 0. Okay, now from this coefficient matrix we will calculate P transpose. How to calculate the P transpose is simply making the rows to the column or columns to the rows. Okay, let us see what is the P transpose here. I am writing that P again here, 0 1 1 1 0 1 1 1 0. From this P transpose is what? Simply you have to convert this means place these columns to the rows. Okay, this is 0 1 1. Similarly for the second column and the third column is turned into rows. Okay, this is the way P transpose is calculated. 1 0 1 1 1 0. This is the P transpose. Okay, now this is the P transpose. It looks same, both look similar. It's not similar, you can say this is same. Okay, how to calculate, the question arises how to calculate the H matrix. Okay, this is the parity check matrix. H matrix is given by, let us take another pen. This is given by P transpose I matrix. From here we can say that P transpose we have calculated. We will substitute here, and there are 3 rows. Accordingly we will have 3 by 3 identity matrix. Okay, let us substitute the P transpose matrix here. 0 11101 110. Okay, and we will attach the identity matrix. What is the order of the identity matrix? Is the P transpose is of that 3 rows. We can have the identity matrix as of the order 3 by 3, 1 0 0 0 1 0, and this is 0 0 1. This is the parity check matrix. We can calculate from the generator matrix, or if you are having the coefficient matrix, you can also calculate from the coefficient matrix as well. Okay, so where is this is useful? From the previous slides we have seen that t greater than or equals to 1, we can correct up to 1 error. For the given example, we can correct up to 1 error. This H matrix, we will calculate H transpose. Okay, H transpose, again the same way how the transpose is calculated. This H transpose we will use to correct the code words. Okay, we will correct the code word, and that thing is called as syndrome decoding. We will deal in the future videos how to correct the code word if there is any error in the code word received by the method known as syndrome decoding. In that, what we will do, the received Y, this is the valid code word. Okay, this valid code word will be multiplied by H transpose, this H transpose, and it will give a vector. This is known as S. This is known as syndrome vector. If is equals to 0, that means all the elements are equals to 0, that means it consists of no error. If Y means the received code word, this is the received code word. Okay, received code word is multiplied by H transpose. Okay, if it is not equals to 0, that means error is present. And if this error is present, then how we can correct that error? We will see in the method of decoding of linear block code known as syndrome decoding. Okay, the next video I will take an example and I will solve how to correct the code word using syndrome decoding. Hope so. With this help of this video, we will calculate, we will be in position to calculate the H transpose, basically the parity check matrix, which is very useful in detection and in correction. I can say in correction of the received code word if there is an error. Okay, thank you very much.